So what we're going to start talk about right now is selective precipitation. And what that is when you have two ions that are sitting there, and then you throw an ion into that solution that both of them want to precipitate out with, one of the two of them is going to precipitate out first. And an example we could do, and it's always good to use examples, let's say I had a container full of water, and this is a clearly delightful container of water, and I have Ag plus and I have Pb2 plus in here. Both these here are positive ions, and one of the things you have to be aware of is that if you have positive ions, both of them have to be positive ions in here. And if you have negative ions, the same thing works. But if you have positive ions in here, what you're going to throw in here is going to be a negative ion. So I'm going to pick a negative ion that I know will precipitate out with both these, and that is Cl minus. And what we know it to be true is this, that both AgCl, if I were to look up the KSPs for both these, and PbCl2, their KSP values, they're different. I believe that, and this is where I could have looked it up before, this is like this blar times 10 to the negative 10, and this is some other unknown number because I didn't bother to look it up, right? But since these KSPs are both different, what that means is that the amount of Ag plus and Cl minus that's allowed to be in solution before they hit this KSP value over here is going to be different than the PbCl2s, which means that one of these two is going to precipitate out first. And then, because of the laws of physics, the second thing will precipitate out. So when we're dealing with AP board type problems, they'll always ask you in a problem, if they have a problem like this with selective precipitation, it's also sometimes called fractional precipitation. I don't know why they decided to do that. They'll always ask you which will precipitate out first. And then they'll say, when, let's say in this case, Ag plus starts forming AgCl. Yeah, let's say that precipitates first. I'm not sure if that's the case, but let's say it did. As this keeps on precipitating out, eventually the amount of Cl minus that you add in here will equal the amount of Cl minus that Pb2 plus needs to reach its KSP. And at that instant, Pb2 plus will start precipitating out. So what they'll often ask you is, hey, this Ag plus has been precipitating out this whole time, so you're losing more and more and more and more Ag pluses, so Ag plus concentrations are going down. And they say, well, the instant that this starts to precipitate, how much Ag plus is still left in there? They'll ask it that way, or they'll say, what percentage of Ag plus do we have at the start? These two questions right here are exactly the same, but the best way to do this is to do a problem. So we're gonna do a problem, and it is an incredibly wordy problem, which I'm delighted with, because isn't that our problem typically when we're reading, when we're trying to do problems, is that they give us things that try and confuse us with words. So let's take this out, and I always really encourage you guys, draw a diagram to try and help you with this. So if you take a look here, it gives you a KSP for BaSO4 and a KSP for BaSeO4, and then they tell you they're adding BaCl2 is adding to these two things. So we have sodium sulfate and we have sodium selenate. Now I'm going to again draw my little beaker of stuff, and because I have sodium sulfate being thrown in here, I'm going to ignore the sodium because that's a spectator ion, and I'm going to have SO4 2 minuses in here. And similar with sodium selenate, I know that the Na2 is not going to do anything, and so I'm going to have SeO4 2 minus. So what I have is I have these two things sitting in here, and I'm going to throw in something into here, and they're throwing in here BaCl2. And again, this could be really confusing because you could look at this and go, they're throwing BaCl2 into here. What's actually going to interact? Well, if you take a look at the Cl, that's a minus, right? Will that minus interact with these minuses here? Let's say no, right? But the Ba, it will react with both these, and it'll form a precipitate. So we're going to just take a look at the Ba2 plus being added in here, and we're going to realize that both of these two right here will form a precipitate with them. Now, the actual equations are kind of written over here on the side. So BaSO4 goes to Ba2 plus SO4 2 minus, and the same thing right here. But I'm going to write KSP expressions for both these. So I'm going to write a KSP for the first equation right here, and it would be equal to Ba2 plus times SO4 2 minus, and they give us the KSP for BaSO4 as 1.1 times 10 to the negative 10. Also, they give us the KSP for this equation right here, and if I were to write the equilibrium expression, which I'm doing right now, even before I go any farther, I can look at this, and do you see how these both are two particles and two particles? In the previous video, we said we can actually compare solubilities via the KSBs when they have the same number of particles. So since they both have two particles, and in essence, this would be x squared is equal to this, and this would be x squared is equal to this if we were doing a solubility problem. Since this value is much smaller than this value is, or not much, but at least smaller, that means that this will precipitate out before this will. This is more soluble, this will precipitate out first. Now, you could go ahead and actually do mathematics in here, because didn't they tell you that they give you 1.0 times 10 to the negative 4 molar of both of these solutions in here? So in our actual container, we have 1.0 times 10 to the negative 4 molar for both of these. So what you could do is you could actually plug in here 1.0 times 10 to the negative 4, and here 1.0 times 10 to the negative 4. And then we'd have Ba2 plus, and we could solve for Ba2 plus in both of these cases. And in both these cases, as we know what they're equal to, whatever one of these two was lower, we know would precipitate out first. Now, we just happen to know, because this is a smaller KSB and we have the same number of particles, that this will precipitate out first, so this Ba2 plus concentration will be less. So that's problem number one. I'm actually not going to plug in and solve for this, but you could, and it would tell you that the Ba2 plus that we have here would be less. Now, the second part of the problem is they ask what percentage of the first thing is left when the second thing precipitates. Will you agree this is the first to precipitate, this is the second to precipitate? Now, if we do the mathematics here, we're going to find out in this case that the Ba2 plus concentration is going to be equal to 1.1 times 10 to the negative 6. That's the amount of Ba2 plus that we need in order for the second thing to start precipitating based on this equation. So we want to know how much of the Ba2 SO4 or Ba2 is left in the solution when the original starts to form. Now, let me show you some mathematics here that you're going to love. Watch. If I take this value right here, this Ba value, this is when the second thing starts to precipitate, and I plug it into when the first equation, wouldn't I be able to know how much of the SeO4 minus is left? Let me say that a different way. We start off in our container with 1.0 times 10 to the negative 4 of our SeO4 minus. But as that reacts over and over again with Ba2 plus, would you realize that we're losing SeO4 over and over and over again? Yeah? While we're still adding in more and more Ba2 plus. When the second thing starts precipitating is when we have 1.1 times 10 to the negative 6 molar of this. So what we can do is we can go to our KSP problem here, which is Ba2 plus times SeO4 minus equal to 2.8 times 10 to the negative 11. And we know that the amount of SeO4 that we're going to have is not going to be the same as the original amount we had, because it's been reacting continuously until the instant that we hit this amount of Ba2 plus. So we can plug in 1.1 times 10 to the negative 6 molar in here, and we can solve for essentially x, SeO4 minus. Let's pretend that that's our x. And so then it becomes, given two variables, let's solve for a third. And when we solve for this, we're going to discover that the SeO4 minus concentration that we have when this amount of Ba2 plus starts is 2.54 times 10 to the negative 5 molar. Now this is kind of interesting, because didn't we start off in this problem with 1.0 times 10 to the negative 4? And now we have 2.54 times 10 to the negative 5, which is less. So this would be typically a stopping point in the problem where they ask you how much of this is left when you start off with this amount. But they ask you one step farther. Don't they ask you for the percentage of the ion that is precipitated? So couldn't we go like this, and couldn't we just go, all right, 2.54 times 10 to the negative 5 divided by 1.0 times 10 to the negative 4 times 100. If you do the math on that, you're going to discover that 25% is what is left, because that's the amount that's left. They don't ask you how much is left. They ask you what percentage has precipitated. So you're going to have to go 100 minus 25 is equal to 75% has precipitated out of the original amount. Yeah? Now I'm going to do another one really, really quickly. It's going to be exactly the same problem, and we're going to do exactly the same steps. This is, if you feel like you're comfortable with this, you don't have to watch through this, but make sure that you note at the very end there's a practice problem that I need you guys to solve on your own. But this is a very similar problem, except here they make it a little bit easier by saying, hey, we just have Ni2 plus and Cu2 plus in solution, and we're adding in CO3. Yeah? So we're adding in these two things in here. By the way, this is a typo. This should be a 3 right here. So one of these two is going to precipitate out first. Now, what should be included in this problem, they did not give it, is the KSB values for these. So I'm going to write these in here. KSB for NiCO3 is equal to 1.4 times 10 to the negative 7. And the KSB for CuCO3 is equal to 2.5 times 10 to the negative 10. I'm going to do the exact same process. Let's do this kind of quickly. I'm going to do the KSB for this and the KSB for this, and we're going to see which requires less. Now, they give us in the problem 0.10 molar of both of these, so we know we have 0.10 molar here, and we have 0.10 molar here. So if we have both of these, can't we solve for X, or solve for our CO3 2 minus in both these cases? Now, before we even go there, aren't these both breaking apart into 2 particles each? So if I take a look at my KSBs, I can actually compare my KSBs when they break apart in the same number of particles. So this is definitely going to precipitate out first, without me doing any math. And since this is going to precipitate out second, what I can actually do is I can solve for the CO3 2 minus that's going to precipitate out. Yeah? So if I'm doing that, couldn't I just take my 1.4 times 10 to the negative 7 and the 1.0 molar and divide that out? And if I do that, I'm going to get for my solubility, or for my X in this case, 1.4 times 10 to the negative 6 molar. That's going to be the amount of CO3 2 minus that I add in to reach when my second thing is going to start to precipitate. Well, they're asking us in this problem, how much of the first thing do we have left? And since this precipitates out first, how much of this Cu2 plus, we start off with a 0.10, how much of that is left when the second thing starts precipitating out with this amount? So what we can do is we can actually, for the second part of this problem, we can actually plug the numbers in for this. So if we plug the numbers in, we're going to end up plugging in the same exact equation right here, our Cu2 plus. And if I plug in my value here for the original 1.4 times 10 to the negative 6, this is when the second thing starts to precipitate. And I know my 2.5 times 10 to the negative 10 is my KSB value. I know that my Cu2 plus, which originally was 0.10 molar, or right now is viewed as was 0.10 molar, cannot be that. So I can solve for Cu2 plus, or X. And when I do that, I get, so clearly we've gotten from here, 0.10 to 1.7 times 10 to the negative 4. Now, they're asking what percentage is still left when the original starts to form, right? They say, how much of the first precipitate in percentage remains when the second precipitate starts to form? We know this is the original amount, so couldn't we go 1.7? And if I do that, I end up with, we have to round to good constituent figures, so we're gonna end up with 0.18% left over. That is not a whole lot. Now, what I want you guys to do is, I've given you a practice problem. This is one of the ones I want you to do on your own, kind of following the templates of what we just did. If you have questions, we'll go back to this. Hopefully this has been helpful. Have a great weekend.